The purpose of this lab was to observe a moving object and to apply Newton's second law to explain the effect of zero net force on it. A Python model which assumes zero net force was used to predict the velocity at set time intervals. Newton's second law explains that a non-zero net force is required to change velocity. The model assumed zero, so it predicted a constant velocity. My observations produced very different results. Our reasoning for using this particular model was that it essentially uses a loop in order to calculate the object's position and velocity at many intervals very quickly. It assumes that there is no net force on the object in order to predict a constant velocity. We're studying Newton's second law here so that we can prove that a net force of zero essentially equals constant velocity. The model is based on this equation for final velocity, which is derived from the original Newton's second law equation F equals ma. For velocity to be constant, the final velocity and the initial velocity have to equal each other, which means that this term right here has to be zero. And the only way for this to be zero, since delta t obviously can't be zero because time doesn't stop, the net force has to be zero, which is why the model assumes that the net force is 0 newtons. The system being studied in this experiment was obviously just the marker right here, which was 13.64 centimeters long and had a mass of 0.0136 kilograms. The surroundings was just the room, which includes the air and the table that the marker is rolling on. As you can see here, the marker's initial position at t equals 0.017 seconds was negative 0.492 centimeters in the x direction and 0.492 centimeters in the y direction. And its initial velocity was negative 59.636 centimeters per second in the x direction and positive 4.969 centimeters per second in the y direction. The only physical part of this experiment was simply this marker being rolled straight across the smooth table while the camera was held still. I'll play it real quick even though it's pretty slow. Now this is just a small chunk of the entire program, but it's kind of the heart of the model, so I'll talk about it a little bit real quick. Now this line right here is literally just the Newton's second law equation that I talked about earlier. To find the new velocity, it takes the old velocity, which is defined somewhere higher up. It's not showing right here. And it multiplies it by that term that includes the net force. And since the net force is zero, as you can see right here, this whole term is going to be zero, which means that the new velocity is just going to be the old velocity plus zero, which means constant velocity the whole way through. Now this line right here is going to take the old position and add the velocity times the change in time to get the new position. It's pretty intuitive. Now the program is going to run these lines, along with some other stuff, of course, in a loop over and over again until it reaches the end of the time period. And yeah, that's pretty much the model. And here are my results. Obviously, there isn't a whole lot of similarity at all between the two. They both move in the negative x direction, but my observations didn't produce a constant velocity like the model. There was a significant amount of acceleration in the positive direction, as you can see by the increasing slope here. I was moving towards the positive x direction. To prevent this and make the model and observation more similar, I could have used a different object or surface, which would create less friction, or I could have used a shorter time interval, which would have a smaller likelihood of experiencing a change in velocity. Now to answer the question of what would happen if we flip the x-axis, the velocity would be equal in magnitude, but only opposite direction. So if this became positive and this became negative, the new velocity would just be like this and like this. It's the same, but only opposite direction. And as for whether we can determine the forces that add to get a net zero in this marker, the answer is yes. The two forces are the forces of gravity pulling down and the force of the table pushing back up on the marker. They point in opposite directions, but they have to be equal in magnitude to cancel each other out. Otherwise, the marker would be flying upward or being pulled down towards the Earth. But yeah, that's lab one, so thanks for watching.